So, can you all see my screen now?
Yes.
Cool. All right. So, yeah, as I said, I'll present some of the work I did with Anthony on models and algorithm for clearing integrated T&D markets. So, with ACOPF and non-convex offers. So, as you may all know, the electricity systems are changing and they are not considered as binary anymore. Indeed, before we had the transmission network mainly producing power that was consumed in the distribution network. But now, with the integration of with the integration of renewable energy sources, mainly in the distribution systems, we have to rethink the way the electricity markets are organized. And some of the ideas we need to think of when reorganizing the electricity markets are typically the fact that now distribution systems must be integrated in the market clearing decision process, that the DSOs, that is the operator of the distribution system, will have a more active role, and also that some of the assumptions that are made in the transmission network are not valid for the distribution systems. And in particular, distribution systems are more complex to model in that aspect. And we can see a lot of projects going on concerning flexibility or T&D coordination within Europe, so NERA, GOPAX, or NODES, for example, also Soteria in Belgium, and other European Commission projects such as SmartNet, Coordinate, or HedgeFlex. And in fact, this work is also part of the FEVER project. So it's a Horizon 2020 project financing the last month of my PhD. It's gathering 17 partners. It started this year and it will end in 2023. Our main collaborator in the project is HENEX, who is the Hellenic Power Exchange. And the role of UC Louvain in that project is to define the relevant market mechanism and to implement the real-time market clearing platform, which is the main topic of this presentation. And some of the challenges that we have to face when taking into account both transmission and distribution are the following. So as I said, some of the assumptions that are valid for the transmission network are not valid for the distribution network, and it especially relates to the physical representation of them. We have to take into account losses, voltage constraints, and reactive power when we model a distribution network. Another aspect relates with the scale of T&D networks. So in this paper of Karamanis, they are clearly mentioned that the number of transmission buses is of thousands, while distribution networks are more gathering hundreds of thousands or millions of nodes. So this changes a lot the scale of the problem that you have to solve. Also, and it has already been discussed during today's presentations, we have to think of privacy and decentralization. The TSO is in charge of the transmission network, the DSOs are in charge of the distribution networks. So, and even if they want to cooperate, there is still some privacy on each of the network to preserve. And finally, one last point that is interesting in this talk is the fact that we need to ensure that prices are coherent and make participants want to stay in the market. And having non-convex physics in the network, but also non-convex structure in the bid that you can insert, complicates how you draw prices in that context. So I just gave a bit of context about the work. I will present how we model the real-time market clearing problem that we need to solve. I will focus mainly on the residual supply function approach that is our decentralized approach that we developed. I will show some preliminary numerical illustration and I will provide some conclusions on the work. hear somebody. If you can please mute your mic. Yes, so I will go ahead. Concerning the assumptions we make in this work, so as I said, we have a TND network, and we are looking at real-time markets. By real-time markets, we are thinking of balancing markets, which is activating transmission or distribution reserves in order to adjust a predetermined dispatch. We will consider a time horizon of an hour, but we have to take the decisions for the next 15 minutes. These time steps are discretized, yeah, as I said, 3 or 4 time steps for an hour, and we need to take the decision for the next 15 minutes. Concerning the network, we will assume that the transmission network is meshed and that we can apply the DC approximation of the power flow equations, and that the distribution network is radial, but we will need the true AC power flow equations in that network. And this is kind of in line with what Leonardo talked about this morning. We'll also assume that there is only one line connecting the transmission network to the distribution system. And on that figure, even if I'm only showing a transmission network connected to one distribution network, the results I will show can generalize to one transmission network connected to several distribution networks. And in that integrated TND market, we have the following actors. So we have the TSO and the DSO. I already talked about them. They have kind of the role you might expect. We'll also assume that at each bus of the network, we'd have MITE prosumers or balancing service providers, as we call BSP, and they can be seen as the flexibility providers. At each location, we might also have a BRP, and you can see them as a price in elastic loads. And we will add a service called aggregation disaggregation service. This service will ideally be handled by the DSO, but this is not in line with what you might expect from a DSO currently. So we keep this service as an extra agent, and it can be handled either by the DSO or another party. And the role of this service would be to aggregate the distribution BSP offer at the TND interface, while ensuring a good representation of the distribution network. And we will do that by using the residual supply functions. And also, when disaggregating the offer accepted, this ADS will have to coordinate with the DSO to make sure that the dispatch are feasible. All right, so to summarize what we want in this work, we want to implement a practical clearing platform capable of ensuring several stuff. The first one being that you want decisions that are near optimal. You want your dispatch to be feasible in order not to violate any constraints on the network. But you also want your prices to be coherent and consistent for all the actors. So LMPs stands for locational marginal prices. Since we are in the real-time context, we want our problem to be solved quickly, so we need to respect a certain time frame. And also, ideally, we want this platform to ensure that the privacy of each operators and generators or loads is met. And the basic problem you need to solve when implementing this platform is AC optimal power flow. So I think most of you are familiar with this problem. We have a network connected with several lines where you can have generators and certain loads. So throughout the whole presentation, the set of buses will be B, the set of lines L, the set of generators J. And the classical variable you have in this problem are P and Q, the real and reactive power injection at each generator. You have the power flow, the real and reactive power flow FP and FQ, and you have the voltage magnitude and angle V and theta. And when you write down your power flow equations, you get the following. But first, maybe I will go quickly through the different quantities you have. So you have the dispatch instructions P and Q, as I said. You have the operational decisions F, P, FQ, V, and theta. You have the fixed load that are determined by the BRPs at each location, so either real or reactive. And this is a parameter. You have also the network properties. So typically, G is the conductance, B is the susceptance, and this relates with the properties of the lines. And what you're trying to do in this problem, so as I said, is trying to minimize the generation costs. You need to satisfy, so these constraints are the power balance constraints. We will aggregate them through using this F function, Fi of x equals 0 for each bus. Typically, the prices you assign to electricity are defined using LMPs, and they can be seen as dual variables of these two constraints. And the last two constraints are the real and reactive flow definitions. And you can see the non-convexities of this problem, which is indeed hard to solve because you have quadratic terms here, a product of two voltages here, and sine on a difference of angles. You also have other type of constraints related to engineering limits. So you want your voltage to be within certain bounds. You want your flow to be between certain bounds also. And this, along with flow definition, relates to operational constraints. So we will use this set to define them. And you kind of have the same generation constraints on your P and Q variable, and we aggregate them using the generations constraints. All right, now that we defined the AC power flow, I said that in the transmission, you can use the DC approximation. And to understand how the DC approximation works, we go back to our basis constraints of OPF. And what you want is a linearized version of the problem, And to get this, we will first get rid of reactive power. We will assume that it's not of importance when considering large networks such as transmission. And we will consider that the conductance is 0. So you might get rid of the terms having G. And the other assumption is that your voltages will be close to 1 and your difference angles are small, so you can get rid of the sign. And after all, if you apply all of the assumptions, you end up with a linear problem. So your real power balance becomes linear, but also your real power flow definition becomes linear. All right, so now we can start to write down the integrated T&D real-time market clearing problem. As I said, we are minimizing generation cost for the whole network, subject to the transmission constraints. So transmission constraints, we start with the power flow constraints at each transmission bus, the fact that the operational decisions are in a certain set of constraints, same for the generation. And we have the distribution network satisfying the AC equations. So we have, again, the power balance constraints, the operational decision within a certain set, and the same for the generation. All right, so now we have written the problem on the transmission network, on the distribution network. We have to link them. So we use this Z variable, which is in fact just the flow between the transmission and the distribution, but we will just write it down as Z. And for ease of modeling, we will assume that this Z variable is duplicated in the transmission and in the distribution. All right, but what we want is also, as I said, is also to take into account a complex bit structure. And to do so, we will introduce one or several variables Yj, which are binaries, in order to model complex bit structure. And in fact, this binary variable will affect the injection PG but also QG, in fact. So I forgot to add also QG for the distribution network. And why do we need binary variables to model that? Because you might think of power injection being modeled as a block bits, or also you can have bits arriving as exclusive bits. So for example, one generator can decide to put 5 bids in the market, but with the constraint that you only can accept one. And to model that in our problem, it only affects the generation decisions. So what we say is that we add this binary variable yj in the process, and it changes also the set of generation constraints on both transmission and distribution side. All right, another aspect of the problem to take into account is the fact that we want this to be solved on a time horizon of 1 hour, so we have a multi-period OPF at the end. So we're trying to minimize the generation costs on all generators and for every time steps. Then we will assume that the intertemporality is only on the generation. So which means that we want our power balance constraint to be satisfied for every time step, and we want our operational constraints to be satisfied for every time step. And as I said, the time coupling will only appear on the generation decisions, and you can think of ramp constraints or minimum duration of a bid activation as being intertemporal. Or also you can think of a storage, but if you want to think of a minimum duration of a bid activation, you can think of, okay, I want or something like this. Right. Then you get a formulation of the complete integrated T&D real-time market problem, which is the following. So you're trying to minimize your generation costs. You have your transmission power balance constraints. I also aggregated the generation and operational constraints as only one set. The same for the distribution, and we also have the interconnection constraints. This whole problem leads to a large-scale non-convex mixed integer problem, and in which we have to determine not only the primal decisions, so xt and xg, but also so part of the primal decisions are also the activation decisions y on transmission generation and distribution generation. But we also need to define the locational marginal prices, lambda t and lambda d. So sorry, I can hear again somebody. If it's possible to mute, please. Yeah, let me do that. Okay, fine. All right. So as I said, now we have a large-scale non-convex mixed integer problem, so quite hard to solve, where in addition we need to define the prices. So the first question to ask is obviously how to solve this problem. And in fact, you can aggregate all of the non-convexities in these constraints, which relates to distribution, which relates to the distribution system. And in fact, ACOPF has been largely studied, and we know that the second order cone relaxation is known to be pretty effective on radial networks, and we will use it for our platform. And when using the SOC relaxation, we will use this TLD notation for the set of distribution constraints. So we came up with two centralized approaches, which are pretty simple to understand. The first one will be the relaxation approach, where instead of solving the mixed integer nonlinear problem, we will solve the MISOCP version, where we will deduce the y variables, then fix the y and solve the resulting SOC in order to deduce x and lambda. This approach is can be solved using a commercial solver, but will not ensure feasibility of the dispatch. And so we'll consider some kind of benchmark where we add this third step, where we want to recover a feasible dispatch when the distribution decisions are not feasible. But keep in mind that these two approaches do not guarantee the privacy preservation, because you will have one operator handling the whole network, and that would typically be the TSO in charge. And this is not a property that is wanted on the market. And to introduce our approach, I will use this small example. So I will present the decentralized approach now. So imagine that you have this small network, so one transmission node and two distribution nodes. You have a generator at each node with different marginal costs, and you want to satisfy this transmission imbalance. So obviously, your distribution BSPs will be cheaper, and you want to use them in order to satisfy this demand. And also, you have a line limit on this line connecting BSP 2 and 3. And when you will solve this problem decentrally, you want to aggregate the distribution network in one node. And this aggregation should be done carefully, and it should be done using this this residual supply function. What is this residual supply function? It's, in a way, the aggregated information of the distribution network. So in this, you will see that you might have 0.5 megawatts coming from this distribution network, then 1 megawatt coming from this distribution network at a 15 euro per megawatt hour cost, and then only the transmission asset would cover for the imbalance. And this trick is the one we will use when developing our framework. So how to do that in practice? So the first step is to build this residual supply function. And what we will do is that we will consider different flow levels at the interface and compute a price in order to be able to build this function, a discretized version of this function. So for that, you need to solve a distribution problem. In this distribution problem, you have all of the classical constraints. You just have fixed your interface flow, and the price you want to associate will be the dual value of this constraint. But in this simplified distribution problem, we assume that use the SOCP relaxation, and that our binary variable are relaxed. And here we're only interested in prices, so we don't need to have a feasible dispatch, and that's why, and that's also something we know, we only need an approximation of the RSF in order to get satisfactory results. Once we've built this RSF, what we will do is use it in order to clear the transmission market. So we have the classical transmission constraints, and we add the residual supply function because we aggregated the distribution information at the TND interface. And we are careful when putting this residual supply function, as this Z variable is defined as follows. From this process, we will deduce the transmission activation and also the transmission dispatch, but also we will fix from now on the interface flow, and we have a price associated with this interface flow. All right, and once we've solved that, we need to disaggregate, so need to find a dispatch for the distribution system, and we will solve the actual distribution problem using fixing the interface flow. So we first solve this problem using the SOCP version in order to get the Y variables, and then use the same problem with the true AC equations and get the dispatch variables. All right, and then we need to do one more step in order to deduce prices for transmission and distribution. And to do so, we will not fix the interface flow anymore and solve one transmission problem and one distribution problem in order to deduce lambda t and lambda d. And this might not be trivial to understand, so I will just use the example to explain why we did this last step. So the optimal solution for this example, as I said, is producing 0 at generation 1, 0.5 at generation 2, and 0.5 at generator 3. And the clearing prices are 15, 15, and 10. And the question is how you can recover the clearing prices. So by doing that in a decentralized fashion. So assume that we have cleared the interface flow and we know that it's -1. The transmission problem is then minimize the transmission costs. We have the power balance at node 1, and we have the power generation at node 1 that is between bounds, and we have fixed the flow at the interface. And this problem needs to the same primal, so to the optimal primal decisions, and you are left with this system of KKTs to solve. And in this system, you have 3 equalities, but 4 variables. So you have a non-unique dual solution, and you might have a non-unique lambda 1, which is not a property that you want. And in order to have access to a unique lambda 1, what you would do, assume that we have the interface, an interface that was the case. So if you look quickly, we had this interface price here. And instead, you will solve the problem, this problem here of minimizing transmission costs with a penalization on the interface flow and without fixing it. And this small trick of solving an extra optimization problem will replace this KKT by the following, where we indeed end up with lambda 1 equals 15. So this was a brief example to try and explain what we did. This gives you the whole picture on the RSF approach. Before moving to the numerical illustration, I just wanted to say a quick word on how to assess a solution X, Y, lambda that we get from the real-time market clearing problem. So it's quite easy to compare the primal decisions because you could think of comparing the objective values. So, but you kind of need to also to evaluate the consistency of your prices. And to do so, we will use the production costs defined as follow, but also we will use the lost opportunity costs. And the lost opportunity cost can be seen as a measure of how much it costs to incentivize a player to stay in the market. And to explain that, maybe we will see what a BSP would do with its generator. So a generator will typically try to maximize its profits, and this is how we define your profit. So you need your generator to satisfy your generation constraints, and you want to maximize the profits, saying that you want the price that is cleared, you want the quantity, you want to maximize your profit. And in fact, if the BSP can gain more by deviating from the dispatch P and Q that is imposed by the market operator, then it will induce a cost for him. And this is how we define the lost opportunity cost. For people who are familiar with this aspect, it's referred as generator side payments for generator and potential congestion revenue shortfall for network operator in Garcia's paper. So I'm a bit over time, so I'm going to go quickly. So we tested the approach on Italian test cases provided by SmartNet. So the first test case is a small one, a medium-sized one, and the two other test cases are pretty large networks with a large number of bits. And here is the results we get. So I reported the three approaches we came up with. So the two centralized and the RSF. Here we have 100 points on the residual supply function. I reported the solve time, the objective value, the percentage of production cost. So this is how far in terms of production cost we are to the relaxation. Percentage on the LOC is how much the LOC represents compared to the production cost, and also the maximum violation of certain constraints, because I need to remind that the relaxation can provide non-feasible dispatches. And so for this small example, as I said, we have satisfying results concerning the RSF. It's pretty close to what you can expect from centralized approaches. For the first large test case, we also get an objective function that is a bit far from optimal, but in terms of production cost and LOC, it stays relatively reasonable. And also you might see that here the relaxation did not provide a feasible dispatch. And we kind of have the same results for the largest test case. And a quick word on the solve time. So something I did not mention, but the RSF approach is highly, we can highly parallelize this approach. And this, between parentheses, is kind of a ideal parallelized solve time. And I also reported the execution time if we had a more realistic number of processors. And you can see that this problem can be solved within a minute for a quite large test case if you have 30 to 64 processors. All right, so a quick conclusion before we switch to the Q&A. So we saw that we have developed and implemented a decentralized approach that is capable of attacking the real-time market clearing problem. And even if the results are preliminary, they are still very promising. And future directions of the work will involve so first elaborating on the results, then try alternative methods for pricing, because for the moment it's mainly relying on the pricing from O'Neill. Also, we have other test cases, test systems like in Denmark, so we want to test it on the Danish test case. And also all of this work is kind of an ideal way of thinking of European balancing markets, and need to be we need to elaborate a bit on how it will indeed be applied in an European context. So thank you for listening, and I will be happy to take your questions.
So thanks, Ilyès. So we have around 10 minutes for questions. So if you have
sorry,
don't hesitate.
Sorry, I went a bit over time.
Maybe I can take the opportunity to clarify a question that came up offline regarding the exclusive bids. If I understand correctly, the platform is supposed to accommodate both minimum up or down time of type of constraints, Ilyès. So
Yes.
if I'm not mistaken, some assets can offer min up down times like you have in usual unit commitment problems, but there's also exclusive products. Is that right? Exclusive
Yes.
offers.
Yeah.
Okay,
Yeah.
just for sake of clarification, because the exclusive offers are more of an I mean, I haven't seen this product definition beyond the EU day-ahead markets. The idea is you take, instead of implicitly describing the set of feasible trajectories of an asset through parameters like min up and down times and P max, P min, for example, you approximate this essentially infinite set of possible trajectories with a discrete set of possible trajectories. Each of them is offered as a take it or leave it product at a certain price to the platform, and the exclusive, mutually exclusive requirement says you can only pick one of these possible trajectories as the one for using this specific asset. So I'm not sure if that helps clarify the question that came up, but if not, feel free to jump in and pose the question.
So if there is no question, maybe I can start with one. So I have a question about your...
I see Alan Marianne has raised his
Alan,
hand,
yeah.
and I suspect I know what he's going to ask.
Yes, I have one question. Do you hear me?
Yes. Yes.
Yeah. Yes. We are.
Thank you for this interesting presentation. And do you think it's possible to adopt such an approach for? You provided some example, but for real case issue where you have a huge size of distribution system combined with the transmission system, do you believe it's a practical way to optimize at the same time in a centralized way those price?
You mean in a centralized or decentralized way? I don't know.
The way you are doing it.
Okay. Yeah. It's true that we are maybe doing a lot of assumptions that are not currently current practice in Europe, but as I said, using a lot of if you have access to a lot of computational efforts and you can, let's say, handle that, then it might be implementable in practice. And in fact, what we know, if I can maybe explain what was the motivation behind this work, is that when we received this data within the scope of the SmartNet project, the first comment was, we are solving this, trying to solve this problem using SOC relaxations, and our execution time were extremely high, and we don't know how to make the computation more efficient. And by implementing these ideas of decentralization, we managed to drastically decrease the solve time. So I think there is room for such practice, but it's true that at the moment, the European energy markets are not modeled the way we did it at the moment, at least.
And in the table you provided, times are provided in seconds?
In seconds, yeah. Sorry, I didn't have the time to elaborate on that. But yeah, they are in seconds, so I reported the solve time. If you solve it, maybe this one is more interesting. If you solve it centrally, let's say. So this starting to be important, and this is also if you solve it sequentially, and this is an ideal parallelized solve time that you can still be within a minute with quite of a good computing, I guess.
If I can add one remark on that, the features of market clearing that make it especially difficult have to do with complex pricing requirements. Here, the whole trick of the residual supply function is that it translates everything that's happening under the feeder to simple bids, essentially. So if we can expect that whatever platform is in place currently can handle a lot more simple bids, those are continuous variables, and what you try and achieve is get approximately right the amount of power that you're flowing on the interface. And once that's achieved in the central platform, then the disaggregation part can cope with a much smaller distribution subproblem. There are many of these, but they're each individually much smaller and independent of each other. So that's kind of how we envision coping to some extent with the scale of the problem.
Okay, so other questions? Apparently not. So me, I have one. It's when you show your second test case, so it's an intermediate size between the two others. And how do you? I mean, what's your intuition of why it's working? It seems to work very well for the first and the third one, and a bit less good on the medium one. No, you are muted.
Yeah, sorry, I struggled to unmute, but now I can talk. So yes, you mean in terms of objective value, right?
Yeah, in terms of objective.
Yeah. So what's happening is that it kind of has to do with the way you discretize your residual supply function. So it's true that, so first thing is that I change, so I have 100 extra points for the last test case because it was even bigger than this one. But yeah, you can refine the objective value that you get if you add obviously points, but this is kind of you need to find a good mix between computational effort and objective value. And this particular, we had this bad objective value, I mean, in a way, because there was some kind of a tricky thing happening in the transmission network in that test case, where if you were not optimal, you end up accepting an offer that is way more expensive than the marginal one you accepted before, and that's why it's kind of difficult to control this effect on the objective value. But I can easily answer this one saying, yeah, we just need to add more points on the residual supply functions that we compute.
Okay, thanks. So maybe there is time for. If not, we can stop here and we have a 5-minute break before resuming.
Yes, we will have this a 5-minute break, and we will be back in 5 minutes with Burak's talk.